Alright, welcome to a very rare late night video. I haven't done one of these in a long time, but I'm feeling pretty good today. Also, I know I have a really good sense of what I want to go through, so it just makes a lot of sense to do a video right now because I can do one quick and really focused. So what I want to go through with this video is this day one deploying MPLS book. I want to do the LSP bandwidth management section, so it's just a few pages. It's mostly going to be a lot of reading, but there will be some hands-on. We're going to learn more about most fill, least fill, random. We're going to learn more about the CSPF calculations, and we will be making some changes to our lab environment. So let's get started with that. So this is LSP bandwidth management. If you are unable to augment your network with both the hardware and physical connectivity necessary to ensure that any given link won't become saturated, or the network has become so large that it becomes operationally difficult to find and utilize available capacity, it is imperative to correctly manage LSP bandwidth in order to help minimize your existing assets. LSP bandwidth management is a method of traffic engineering. It spreads the traffic over the available resources. While bandwidth management is a subset of traffic engineering, it is covered. Oh, the sprinklers come on at 9, so there's a weird noise that happens at 9 every time because it sounds like a snake, which is why it always surprises me, but it's just the sprinkler system coming on. LSP bandwidth management is a method of traffic engineering. It spreads the traffic over the available resources. While bandwidth management is a subset of traffic engineering, it is covered in this dedicated section because there are many features and techniques available. Because bandwidth management focuses on optimizing existing resources instead of adding capacity along the most optimal path, some traffic may not take the most optimal path through the network. However, in a resource-constrained environment, it may be more important to ensure that traffic reaches its destination rather than arriving there via the most optimal path. Static LSP bandwidth. It is possible to allocate a specific amount of bandwidth for an LSP so that when the ingress router signals the LSP, a specific amount of bandwidth on each link becomes reserved for that LSP. In the example output below, the LSP Lagavulin to Oban and Lagavulin to Oban Prime. It's kind of interesting. I wonder if these are cities. I'm pretty curious about. Ah, yeah, so it is a city. So it's a city in the United Kingdom. Let's get some. Let's see how long it is to walk between these two cities. Oh, so it's going to be it's going to be impossible because you got to cross the water. So you're going to need to drive. You probably even fly because now you're probably going to want to drive. So there's just a huge bridge here. That's interesting. It's kind of an interesting bridge. I'd like to see some photos of this bridge. Well, anyway, let's stay on topic though. Oh, it's probably a ferry actually. It's probably not a bridge. Yeah, it's a ferry. Yeah, because that would be too big of a bridge. Alright, so let's stay on topic here. In the example output below, the LSP Lagavulin to Oban and Lagavulin to Oban Prime each reserve 150 megabits per second of bandwidth. This is a constraint when the LSP is signaled. If a path does not exist with the available bandwidth, then the LSP fails to come up. Okay, so let's make these two label switch paths, but we're going to use a different destination. Our destination will be to PE2. Oops, so it looks like I've already got GNS running, so yep. There it is. So let's delete the LSP from PE1 and then reconfigure the LSPs here, except with a different destination address. Now remember, these are going to be RSVP signaled LSPs just by nature of them being statically configured like this. That's basically the point of RSVP, is you can make your own custom configurations for an LSP, and they're not created automatically. The point, when they're created automatically, it is by way of LDP, Label Distribution Protocol. Okay, so here's everything we've got. Let's delete the existing, oops, let's do another edit based on what we've got on here. So during the lunchtime video, I would clear off the LSPs to have it go faster because I could not wait this 120 seconds, but it looks like the reason it takes that long to re-optimize the LSPs because I have this manual configuration here. So let's change that to something like 15 seconds, something I can sit and wait for without too much problem. Okay, so it looks like the minimum is 0 seconds, so we'll just do it forever. Let's do, how about 10 seconds? And then we can watch it run those calculations again. Alright, so now let's delete the existing label switch path, which is named PE1-PE2. Okay, and let's make the two paths that they have here. So it's going to be label switch path Lagavulin to Oban. Okay, and I'll go into the hierarchy mode for this. And it's going to have the same 2 as the previous label switch path, but it's going to have a different bandwidth. And it's going to have a primary, and it's going to be via Blair. Okay, so I don't think this will commit yet, because let me do a commit check before I configure the other part, because I don't think that primary statement is going to work. Yep, because this path via Blair is not defined. So it looks like we've got 2 paths. One is via Blair and one is via Talisker. So let's pretend that this path PE1 to PE2 to PE3 is via Blair, and PE1 to P1 to PE2 is via Talisker. That way they'll be the same amount of hops. Okay, so let's go into, let's do a printout of the candidate config, and let's go into protocols MPLS. Or actually, before we do that, let's get rid of the SLRG, because that's leftover config, so we'll just delete all of the routing options. And then let's get rid of the subscription statements. Okay, so now let's set our path, primary via Blair. So we're gonna, I believe it's under protocols RSVP, but we'll find out. Nope, so it's not under protocols RSVP unless it's under the interface. Okay, so I wasn't sure about that. I actually think it's under protocols MPLS. Perfect, yep, so it's path. So let's create a path with the name used in the book here, which is going to be via Blair. So now we need to specify the address of the next system in the path, and in our case we're going to have that be P2. So we'll use this interface here to define that. So I'm going to look that up. Oops, I work on different kind of gear at work where there's no show configuration, so if I'm doing a video right after work, I'm probably gonna get that wrong. Okay, so this is going to be the address of the next system in the path. Alright, so now let's configure the other LSP. Okay, and this is going to have the same 2 as the previous one. So I will copy that. In fact, all of that configuration is going to be the same except for the last part. And it's only different in that it uses a different path. So just as before, if I were to commit this right now, I would get an error because I haven't defined the path. So let's do that. Okay, so now we need to give it the next hop, and it's going to be router provider 1. So let's look up the address. Okay, so with any luck, we're going to get a successful commit now. Perfect, so let's continue reading. It can be a fairly useful, if static, tool. It reserves bandwidth on each transit link, but manual updates to each LSP's bandwidth are still necessary if the traffic on the LSP continues to grow. Additionally, it may be inefficient to statically reserve a large amount of bandwidth for an LSP for future growth if that LSP only needs to carry a small amount of traffic in the near to mid-term because that bandwidth reservation may consume bandwidth needed for other LSPs. This option may be acceptable for an LSP that carries a constant, easily predictable amount of traffic that is not expected to grow very much, if at all. Happily though, the Junos OS offers more dynamic options to manage LSP bandwidth. Automatic bandwidth allocation. Automatic bandwidth allocation, unlike static LSP bandwidth, allows an RSVP LSP to dynamically adjust its bandwidth reservation based on the amount of traffic it is carrying. Traffic is moved from the old path to the new path with the modified bandwidth allocation in a make-before-break fashion. The ingress router signals a new LSP path with the modified bandwidth, and if the path successfully comes up, the router moves the traffic from the old to the new path. If there is not adequate bandwidth for the new path, then the current path and its current bandwidth reservation remain. This means that automatic bandwidth allocation does not impact traffic when a new path is signaled. For instance, an LSP can be configured for minimal reserved initial bandwidth and then use automatic allocation to adjust its reserved bandwidth based on actual usage without experiencing packet loss during a transition. Note, the allocated bandwidth is not necessarily the maximum amount of traffic that the LSP can carry. Rather, the allocated bandwidth is simply the amount of reserved bandwidth on any given link that the LSP traverses. If the links along the LSP's path are not saturated with actual traffic or reserved bandwidth, then the LSP can carry as much traffic as necessary until there is bandwidth contention on any given link. In order to prioritize certain traffic during periods of congestion, class of service must be implemented, which is beyond the scope of this book. Which is kind of interesting because class of service is in the same scope as MPLS, at least if you're studying for the IE. The first step in enabling automatic bandwidth allocation is to configure MPLS statistics with the auto bandwidth option. The interval, specified in seconds, is the amount of time used to calculate average bandwidth usage. Alright, so let's enable this. I'm not sure if it's related to bandwidth constraint configuration, but I think it still might be good to know. I am pretty satisfied with the work we've done so far to study for bandwidth constraint configuration, however. Let's take a look at the help menu for this. So this is collect statistics for signal labeled switch paths. Okay, so let's see what kind of options we've got. Quite a few. We're going to need the auto bandwidth statistics. We're going to need to save it to a file. Here the interval is set for 600 seconds, 10 minutes. The configuration allows Lagavulin to collect the traffic statistics needed for each individual LSP's periodic adjustments. Once the router is configured to collect MPLS statistics, automatic bandwidth allocation must be enabled on each desired LSP. To enable automatic bandwidth allocation on an individual LSP, configure the auto bandwidth keyword. And I'm still curious about this because it looks like it's a real name of a real city, so I'm kind of interested how it's so I was pretty much right. It sounds like instead of Lagavulin, it's Lagavulin. So I would kind of put the emphasis on the U, but it seems like it's all kind of at the front, and then the back kind of flows out. So it's Lagavulin instead of Lagavulin. It's Lagavulin. Oh, well, I thought it was that might just be, he might just be saying it weird for the whiskey commercial, I don't know. But Lagavulin is how I think it is. It's probably better than Lagavulin. Once the router is configured to, yep, I already read that part. So let's go to the label switch path and enable auto bandwidth adjustments. Okay, so we set it to be 10 minutes, which of course is going to be a lot longer than I'll be able to do. So we might need to go back and set that to a lower interval. I'm going to bump up my mic a little bit here. I seem to be speaking a lot more softly now that it's late at night. Okay, I think this is better now. So we've got, yep, the same stuff we already did, so let's add the new configuration. We're just going to add it to the Lagavulin to Oban label switch path. I forgot the ED. Okay, so let's go into the mode. So we're going to do auto bandwidth allocation for this LSP. Okay, and let's read the descriptions of each of these commands. The first one was adjust intervals 7200, bandwidth reallocation interval. Default is 86,400 seconds. So really large interval there by default. Adjust threshold 20 specifies the sensitivity of the adjust threshold. This is optional. Minimum bandwidth 64K, optional. Min bandwidth reservation for LSP. Maximum bandwidth 150 megabits, optional. Hard max limit bandwidth reservation for LSP. And then of course we've got our regular primary path. Let's take a look at all of the configuration we've got so far. Yep. Alright, so I'm going to commit that and then continue to read. Tip: it is considered a best practice to explicitly specify the values of the MPLS statistics interval and the LSP's auto bandwidth adjust interval, even if you are using the default values. Doing so helps to act as a reminder or a notice to operations and engineering as to what type of behavior to expect from automatic bandwidth allocation and when to expect it. The interval above shows automatic bandwidth allocation configured for the LSP Lagavulin to Oban. Enabling this feature for the LSP only requires the auto bandwidth keyword. but other options in the auto bandwidth hierarchy are configured to conform to best practices and to demonstrate the different capabilities of the available options. As configured above, here is the behavior of the automatic bandwidth allocation for the Lagavulin to O-band LSP. The average bandwidth on each LSP is measured every 600 seconds, or 10 minutes. The configured adjust interval value of 7,200 means that the Lagavulin to O-band LSP can adjust its bandwidth allocation every 7,200 seconds based on the traffic statistics for that period. The LSP's adjust threshold is 20%. If the current bandwidth allocation for this LSP is 100 megabits per second and the bandwidth demand increases to 110 megabits per second or decreases to 90 megabits per second, 10%, the LSP's bandwidth allocation is not adjusted. But if the bandwidth demand increases to 125 megabits per second or decreases to 75 megabits per second, 25%, then the LSP bandwidth is adjusted to 125 megabits per second or 75 megabits per second, respectively. The LSP will have a minimum of 64 kilobits per second allocated bandwidth and a hard maximum of 150 megabits reserved bandwidth. Tip: when configuring the LSP's auto bandwidth adjust interval and the MPLS statistics interval, it is a best practice to set the LSP's auto bandwidth adjust interval to no less than 3 times the value of the MPLS statistics interval, or to put it mathematically, 3 times MPLS statistics interval is less than or equal to LSP auto bandwidth adjust interval. This minimizes unnecessary LSP resignaling by ensuring that the LSP has a minimum of 3 MPLS statistics batches to draw upon before deciding if it needs to adjust its bandwidth allocation. Warning: at the time of this writing, some of the Juno's documentation up to and including 10.0 incorrectly indicates that the LSP auto bandwidth adjust interval should be no more than 3 times the value of the MPLS statistics interval, 3 times MPLS statistics interval greater than or equal to instead of less than or equal to LSP auto bandwidth adjust interval. This is being remedied, but the remedy date for corrected documentation is unknown at the time of this writing. Alright, well that's good to know. There's an error in most of the documentation out there where this sign is displayed incorrectly. This is how it's displayed in the erroneous config, but it's actually meant to be less than or equal to. Monitor only in the event that you only want to monitor an LSP's bandwidth but don't want to have the router make automatic allocation adjustments. Use the monitor bandwidth keyword in the LSP's auto bandwidth stanza. So before we do that, let's take a look at the MPLS LSP. And we're going to give it a name here, narrow it down. Alright, so let's just start with that, and then if we need more detail, we'll get it. Yep, looks like we're going to need more detail, so let's do detail keyword. Yep, and this looks really familiar. I've seen this before. So it looks like now we've got a optimized timer, and we've also got a smart optimized timer. And of course, it's no longer in a SRLG. We've got auto bandwidth enabled. We've got our adjust timer, all of our specifics to that are right here. Let's do a monitor MPLS, monitor start on the MPLS T-shoot fob. and see if anything comes up. So there will be, yep, so this looks like, okay, so this looks like it would have run CSPF, but there were no changes, so it decided not to run it. Now we should see some chatter every 10 seconds because of a timer I set. Let's take a look at the configuration and see what some of the timer values are. Yep, so we've got this optimized timer every 10 seconds. So we can see this is August 02, so we should get something new at 0212. Let's just sit on it for a little bit and see what comes up at 0212. Oh, sorry, not 0212. We should see it at 45 instead of 35 because this is the minutes, this is the hours. Yep, so perfect. We got it at 4.5. We'll also get one at 5.5, and it looks like the messages we get are these CSPF calculations, but they're not going to happen because there were no changes to the traffic engineering database. But these are the messages we're going to get every 10 seconds when we set up these optimized timer. When we set this command here, we're going to get those messages popping up every time this timer expires. And we'll get a lot more messages too, dependent on other timers. These interval timers here, but they're not going to be frequent at all. I'd be surprised if I even saw them because 10 minutes is a long time. Let's move on and configure the adjust interval and the monitor bandwidth statements on the other LSP. So the first LSP we're going to be doing auto bandwidth, but the second one we're just going to be monitoring, but not actually applying the changes. Oops, so we've already got some configuration on there. Let's see what we got. We got the to statement, we got the bandwidth statement, and we got the primary statements. So let's just focus on the auto bandwidth statements. Okay, so every 86,400 seconds, we're going to be doing these adjustments, but instead of applying the results of calculating what kind of adjustments are needed, we're just going to monitor them somehow. So I'm not sure what that means exactly. Are they going to be written to a file? Hopefully we'll find out. In the above output, Lavagulan to Oban Prime, LSP is monitoring its allocated bandwidth, but is not modifying its allocated bandwidth. This is called passive bandwidth utilization monitoring. So let's take a look at the differences between the first one and the second one. So I don't see anything different here. Let's take a look at the difference between the detail. So again, I really don't see any differences. I do see that this second one has monitor utilization on it, but I don't see where we can get those stats. Yeah, it probably takes a different command. Let's try to find that command. I have a feeling it might be something like statistics. Yeah, so it looks like we don't have anything special here when we use the statistics keyword. We don't have it here either. So yeah, I'm not sure how to see the results of passive bandwidth utilization monitoring. But let's just move on. I don't think that's going to be a big deal. And we've got quite a bit more to get through. In fact, I might need to end the video and devote another video to this. I kind of hate to do that, but it might be necessary. Manual bandwidth adjustment trigger. Junos allows a user to manually trigger an automatic bandwidth allocation adjustment for all LSPs configured for auto bandwidth or just specific LSPs with that configuration. This can be useful when testing automatic bandwidth allocation in a lab or when the LSP is configured for passive bandwidth utilization monitoring and you want to initiate a bandwidth adjustment. Initiate an immediate automatic bandwidth allocation adjustment with the operational command request MPLS LSP adjust auto bandwidth. I kind of wish I had known about this section of it before, because then I don't gotta sit around and wait. Let's start that file here, and oops, it looks like we can even give it a name. But let's do a monitor start on the MPLS hierarchy, and then do that request. Okay, and yep, let's just do it for all of them, and hopefully we'll see a lot of interesting chatter. Yep, there we go. So this is, here we go, so trigger manual auto bandwidth adjustments. It's going to do it for both of them, I believe. So completed the job. Yep, and it didn't need to make any adjustments, so. Yep, MPLS LSP update complete, but it didn't need to make any adjustments. Without the optional LSP name, the command invokes the adjustment in all LSPs configured for auto bandwidth. If the user includes the optional regular expression for the LSP name, then all LSPs configured for auto bandwidth whose names contain the specified regular expression automatically adjust their bandwidth if the criteria for a bandwidth adjustment have been met for the individual LSP. Note, when a manual trigger for automatic bandwidth adjustment is used, the adjust interval timer on each affected LSP is not reset. So auto bandwidth in action, an example. Let's stop it here, and then during the lunchtime video we'll do another video on this. Kind of a bit much, but I kind of feel like I'm learning a lot, so it's, I think it might be worth it if this subject comes up on the test. But for the next video, which will be video number 4, we'll continue where I left off just now. Alright, but that's going to be it for now. I'll do a monitor stop so that it's not chirping the whole time. Alright, so thanks for watching, and I'll see you in the next one.